Hello, everyone. Getting back to it. Getting back to the Texas voting data. If you remember last time we left off, we were plotting voting districts of Texas. We made this really cool map using the shapefiles from the Texas Legislative Council. We joined that data. Well, first we aggregated it to the county level, and then we joined that data with some Texas voting data and plotted the turnout proportion in the 2024 general election. We were just doing some rough plotting. See that things aren't really labeled here. We did some rough plotting, not really changing the colors or anything like that, just to get a feel for the package we're using, which is the library SF. And we're using that to manipulate the shapefiles, make some of these plots. And we're trying to create a framework for understanding, eventually, of making something like a dashboard to plot historical election data, which we've downloaded from the Texas Legislative Council. And after we can look at the historical data, we're going to think about ways to make some models that predict or explain, perhaps is a better word, explain the dynamics of the census data, that is the demographic makeup, as it relates to turnout, who voted for who, all that stuff. So let me just get the stream going. I'd like to open the chat window. And then we can get moving. So let's see. I want to get the link for my stream. We are live. A link for my stream. Right. Right. Taking it away here. So we can see our turnout proportion map. So what's this all about? That's the real question. What's this all about? What are we actually looking at today? We made this turnout proportion map. We have this shapefile. Let's just take a look at our file here. Oh. I'll run some of these things. Closed our studio, so we have to load everything into memory again. There we go. I don't really want to plot that again. It takes a while. Here's our county union. It takes a second to do this. And these were some of the things we were thinking about yesterday. Well, it takes a second to union all the voting districts into counties. So if we want to plot county level data, we probably want to have that stored, not at the simply voting district level, and every time we choose to plot the counties, we re-aggregate them, because it takes about 5 or 10 seconds. plotting the counties is pretty fast. It's not that fast, but it's pretty fast. And we have some general election data. Here we're joining it with the county level data. Here we're reading the turnout data. Here we're joining the turnout data with the county level data. And here we're plotting the turnout proportion. All right. I'd like to read in some of the demographic data now. We're going to use the 2020 census data, which we have downloaded already. We did that yesterday. We got it from the Texas Legislative Council website. So we've got data, Texas voter data. And 2020 census geography. Shift click, copy as path. Control Alt I opens a new coding window. And we're going to say demo 2020. What kind of files do we have? Still zipped, isn't it? We have to extract this stuff. Block groups. They're all census delineations of different levels of aggregation of census data. The census tracks their data in a variety of different ways related to cities, counties, blocks, and block groups. And these are all different sizes, different levels of aggregation. Counties is straightforward. We all know about that. Blocks and block groups are smaller units. They don't typically release data down to like an individual person, but they will release data for smaller regions they refer to as blocks, and multiple blocks make up a city, a county, etc. I'm extracting this, but we're not really going to be able to use this data because it doesn't correspond with voting tabulation districts, and it doesn't exactly correspond with counties. So although we would like to make some inference about the behavior of people in voting tabulation districts, the census data we have is aggregated up to the county level. So if anytime we're using census data, we're really going to be using county level census data. Not sure what CDPS is. extracting all of our census data. Even though we'll probably only be using the county level data. Now we could use city level data and aggregate the voting tabulation districts. It seems likely that the cities and the count, like, we'll probably be able to join back and forth between these units. So see how that goes. We have census tract. I don't know exactly how those fit into the aggregation level, but the common census unit. Right. So let's just start with the county level data. Or shift, right click, copy as path. And I'm going to save. We have to change the slashes because R likes forward slashes and Windows likes backslashes. The file we want is this counties.shp file. We're going to use this function stread from the SF library. We're going to read our file. Have to actually do it all. There we go. And let's look at the projection that each of these data sets are in. The census data is in NAD 1983 Lambert conformal. And we can see that our election data is also in the same projection. So that's really helpful. That means we don't have to do any transformation when we want to plot the census data. We can just join it directly, either way, to our voting data. And let's take a look inside the census data and see what's in there. Use this glimpse function, that's from the tidyverse. And we have a FIPS, we have a county key. So we're going to have to join based on this county key. And if we look back at our voting shapefile data, we can see that we have this CNTY variable, and almost certainly that's the county key. Oh no, we actually have county key here. So maybe those are the same, maybe they aren't, but we do have county key. And so we'll be able to bring it in. And the very first thing we can do is just get the county name, which is going to be very helpful if we want to pull up specific information about a county. Do that. We're going to look to, oh, what's the name of it? We're going to join our county data. It looks like the census data that we've downloaded only has Texas data, right? The reason I say that is because this shapefile has 254 rows, each one representing a county. That's the number of counties. To the best of my guess, I'm just guessing it's the number of counties. I don't know for sure. But it seems like a number that makes sense. So let's see if these files are going to conform to each other. They will, right? So this is our county shapefile from the voting data. It has 254 rows. This is our county shapefile from demographic data. It has 200 rows. Good, even Steven. Now I will notice that this is not in order. Okay. Shouldn't be a problem. Something I'm going to do though is group by county key. I'm going to try grouping by county and county key. Hopefully we get the same number of rows. And then we can use the same field to join our demographic data. If we get more fields, that means county and county key do not correspond one-to-one, but one-to-many. And then we'll have to figure out what we want to do there. The solution could be just to group by county key when we're counting votes. But we may want to explore that a little bit and understand where those are different. But they're not different. They are different, actually. County and county key are not the same. We can see they have different values. But we do have the same number of rows, indicating that they are distinct, which is good. So now to join our shapefile, all we have to do county shapefile general election 2024 turnout demographic data. We're going to enter join. That file, our original turnout data with demo 2020 SF. And we're going to say join equals join by county Y should not have class SF. What class is this? This has class SF, so X has class SF. Does demo 2020 SF not have class data frame? It does. Well, this is interesting. So one way we can solve this is by removing the geometry from our demographic. Curious, or I'm intrigued why this worked earlier and it didn't work here. So we look at all these other shapefiles. They all have the same classes. Oh, but I did use that one first, so let's try this. Try switching the order. Maybe the order has. Oh, I used the keyword join again when it's by. That's the problem. No, it still wants me to use a spatial join. What is that? County key is not a spatial field. I don't really understand why it wants me to do a spatial join. when it didn't ask me to do that here. Like we can look at the class information for these. Turnout 2024 is of class data frame. Does that have something to do with it? Okay. Very peculiar. And if I look at these, okay, so this inner join method can only be used when one of the objects is of class data frame and the other is of class shapefile. It cannot be used to join two shapefiles. Pretty interesting, actually. So in order to get around this, we are going to specifically type the demographics file as a data frame. And it has to be in the Y field, it looks like, and it's in the X field right now. So we are going to swap those back around. And this should work. It does. And we have two geometry fields, Y. I did specifically remove the geometry field here. I think I have to select minus geometry after I could do the type conversion. Try that. That gets us what we wanted. Okay. So now our geometry is coming from the voting data file. We can see type polygon here. We have these polygon objects. See the written text form of those objects written out in the tuple pairs, point pairs, designating easting and northing coordinates. We have the turnout proportion for every county. We have the FIPS code for every county, and we have the name for every. Now, if I wanted to do something like look at the voting tabulation districts in a specific county, remember it was a bit slow to plot the entire voting tabulation district for the entire state. And we couldn't really zoom in. There was a lot of fine detail around the cities and those urban voting tabulation districts that are quite small that we couldn't observe. But if we wanted to look at some of those, we could select them out individually and then maybe plot just, say, the voting tabulation districts for Travis County. So the way that we would do that is by looking, what is the name of our voting tabulation? I think it's, okay, the voting tabulation district is SF 2024. And we look at SF General Election 2024 with turnout. I think this has all the turnout data for every voting tabulation district. Just take a look at that. Yeah, we have that. So basically what we would want to do is join our county names with this file. Something like, now during this exploration phase, things are kind of getting jumbled together. We're joining a bunch of stuff, we're looking at it as a plot, we're looking at another data set, and we're joining a bunch of more stuff. When we want to create a dashboard, we're going to have to refine that and make some decisions about the order of joining. We don't have to do that yet, though. So here we're going to, what are we going to do here? We're going to join county names with BTD data. We'll just try to keep some labels in our exploration file so that when we go back, we can identify what's going on. So I'm going to do a different strategy for the join here, just because it's fun to do stuff differently sometimes. I'm going to use the magritter pipe. I've been using this pipe or this pipe operator a number of times. It's a very handy operator. And when I call it a pipe, it's because it operates in a pipeline. So it takes whatever comes before, puts it through the pipeline to whatever comes after, and then you can daisy chain these pipelines together. For example, right here, I took the demographic shapefile, I turned it into a data frame with the pipe command, and then I took the output of that, a data frame, and removed the geometry. So it's just a nice, easy way to do step-by-step operations with data. Okay, so here we have our shapefile general election 2024 turnout, and we want to inner join. Want to inner join? I mean, I guess we can. Another way to think about this operation might be a left join, but I'm pretty sure that since all the counties are in the previous data set and all the counties are in the demographic data set, that this should be a one-to-one relationship. We can check that afterwards by just looking at the number of rows in the resulting join. All right, so inner join, demo 2020 SF. Actually, yeah, but we're going to have to do this conversion again. I could have used this file, but in the framework of our script here, of our program, this file is generated in part by this file. So it's a little messy, that's a little unclean. It might be hard to follow later on. So I'm instead just going to use this method. And then we say by, not join. We're going to use county key. And I can save an R at the end of a line as well as at the beginning. So I'm going to use the arrow to put this in SF GE 2024 turnout. I'm just going to call this plus, and I might add more stuff to plus, or we'll call it featured. Sure why I complain. Unexpected end of doc. Yeah, that's fine. All right, so if we look at this file, it'll have our county names. We can see we have some duplication, shape area, shape length. One of those is from the county file, and one of those is from the voter turnout file. So let's clean that up a bit. There might be a way to use a keep. Let's see, can't remember. So it's adding this suffix to columns that share a same name. Also this field keep. So if null, the default joins on equality retain only keys from X, while joins on any quality, retaining keys. Okay, so these actually aren't keys in the join. Right, so we're going to have to drop them. We'll drop them at the same time we drop the geometry. Actually, it might be cleaner here to select what we want to keep. And what we want to keep is county key, FIPS. That might help us join more demographic data. FE name, that's the county name. I think that's all. Much cleaner. All right. So now we have the county name. And what we're going to do next is plot a single VTD turnout. Not a single VTD. Plot a single count. Plot VTDs from a selected county. Plot turnout in VTDs from a select. That's what we're going to do. Righty. So what do we want? How do we want to do? We're going to say, you can imagine we have a drop-down menu or something, and we select a county by name, or we type in a county name, right? So that send command to our data set that looks something like this. A little too much. Actually gonna select turnout above here. So we just comma select. 3, 5, 7. There we go. Turnout for Travis County by voting tabulation district. Now, what we don't have is the proportion. And that's kind of what we want. Now, voting tabulation districts are getting towards something that's kind of like equal size. So the colors here are actually quite distinct, but we'll see if that's actually, if that holds true. Because we want to look at turnout as a proportion of registration. Use this command. But since we haven't aggregated, it's going to be a little different. We're going to do it in a single step using the magritter pipe like we did before. And we're going to do turnout proportion equals turnout divided by voter registration. Go. Pull it up on the big board. Here we go. Nope, that's still the voter turnout because number 14. So last one, 20. Isn't that interesting? So it's not homogeneous across the county, homogeneous, but it is regionally very homogeneous, isn't it? Now something I know a little bit about the geography of this county and the demographics. So these tight voting tabulation districts, this is downtown Austin. This is South Austin. This is like the South Congress area. This is down I-35. East of I-35 is more rural, and also more Hispanic. North of Austin, up to about this line right here, that is, I believe that's approximately where 183 is, and that's a pretty wealthy area of town. Here to the west and near Austin is Westlake Hills, very well. That's the most wealthy area in all of Austin. You can see the voting turnout's the highest there. North of 183, this is like the North Lamar area, very Hispanic neighborhood, also some there's a lot of Asian neighborhoods there, I believe. This line, this strip, I believe is 35. East of 35, even in North Austin, tends to be more Hispanic. The near East Austin, like this area, is the revitalized, historically, this is like a gentrified area, basically. And it's interesting that voting totals are low there. North Austin into the Pflugerville area, Pflugerville and Round Rock up here. The Pflugerville typically is sort of like people who can no longer live in Austin have moved to Pflugerville, sort of thing. And similarly for Round Rock, although Round Rock tends to have its own kind of urban center, kind of more conservative in Round Rock than Pflugerville. Also more white. Here west of Westlake, we have like the Steiner Ranch, Lakeway area, and west of that we get into the rural hill country. And so that's what we're looking at here. Out here we're looking probably like the Pedernales Rivers out here, and Pedernales Falls State Park, Hamilton Pool, Reimers Ranch, stuff like that. Bee Cave Lakeway. I believe Lakeway is this yellow strip right here. It's a little bit hard to see because part of this is water. So it gives the illusion of these big voting districts, but most of these big voting districts are mostly made up of Lake Travis. So, yeah. So we can see out west, where wealthy conservative people live, there is very high turnout in this election. Extremely high turnout. South of Austin, extremely high turnout. And east of Austin, where traditionally more Hispanic people are living, is very low turnout. Pflugerville, very low turnout. Not sure. This might be Lago Vista. I don't know. It's interesting why this, maybe just from an access point of view, why this voting district, these two voting tabulation districts, have a lot less turnout. Be interesting to look into that. Now we can look up directly the Spanish surname voter registration counts and see if these correspond, how they map onto the turnout, right? That'd be interesting to look at. Oh, we have Spanish surname turnout. Very interesting, very interesting. You can see it's quite low just by a quick scan of these voting tabulation districts. Just by a quick scan, Spanish surname voting turnout is below 20%. It's really kind of remarkable that it's so low. Below 10% in some voting tabulation districts. It'll also be interesting to see how that corresponds to these demographic or these regional demographic factors, right? What's Spanish surname voting turnout in Westlake Hills? There are Spanish people that live, Spanish surname people in Westlake Hills. Let's see. Let's see. So instead of voting turnout, we're going to plot 19, 18, 17, 16. We're going to plot Spanish surname voting turnout. Wow. That is really amazing. So if you live west of Austin and you have a Spanish surname, you didn't vote. Wow. Like these can't possibly be zero, right? Let's just see if there are any zeros. There are some that are zero. I'm curious where those are. Plot Travis County VTDs with zero Spanish surname voter. Okay. This graph is remarkable, isn't it? Like, whoa. Because there are Hispanic people that live in a lot of these areas. There are. Why don't they vote? Actually, before I do this, okay, there's a command I can use, which is like par mf row equals. Let's do something like this. Rows and column. I want to plot two things next to. I think that's the right command. Not sure. We're gonna find out. Spanish surname voter turnout and Spanish surname voter registration. Decent. Did not work. Okay, it didn't work. But voter registration. Okay. So not only is the turnout extreme. Wait, turnout. Oh, okay. This isn't exactly. We want Spanish turnout proportion. So we're jumping to conclusion. But okay, and then it'll be 0.1. that real? That can't be real. Okay, wait a second. Turnout is stored as a proportion here. But turnout is stored as a... So this is something that's interesting about data and data organization. Oftentimes, whoever's working on data, or maybe multiple people are working on data, and they don't save information in the same way. So in this file, turnout is saved as the number of voters who turned out. And that corresponds to the number of voters who are registered. But Spanish surname voter turnout is saved as a proportion. So presumably, even though these are both called turnout, this one is actually the proportion of turnout, and this one is the absolute number of turnout. Now, it's not actually that great, because when we only have the proportion of turnout, we lose the information about how many voters actually... Now, we could back calculate it, presumably by multiplying these numbers, and maybe get the number of Spanish voters that came out. But just a little thing that happens with data. When multiple people are working on data, you get these little things that, like in this case, turnout doesn't mean the same thing as turnout when we're considering a Spanish surname. Just an annoyance more. But now we know that. I was concerned that I was actually looking, like I said, we were jumping to conclusions because I thought, oh, actually I plotted the raw numbers, but no. I need to quickly refresh myself on how to plot two things side by side. I want to plot two things side by side in R. We fix this code. Oh, it says it's correct. Okay. Well, if it's correct, then why didn't it work, you know? It must have to do with the plotting method of SF. So, Spanish voter registration. Okay, in certain areas. Well, I mean, a lot more people live there, you know, so maybe it's not okay. But this turnout plot is really remarkable. Hispanic people living west of Austin just don't vote, period. And that's among people who are registered, right? Like, we have registered voters out there, they just don't vote. Fascinating. Even areas up here by Pflugerville. Like, look at this. This is Pflugerville. No voter turnout. It looks like all of the voter outreach is happening in southeastern Travis County. I think this is mostly just a function of where the voter outreach people live. They live in Austin, so they work in southeast Austin. It also takes a lot more work. It's a lot more rural out here. You have to drive around. I mean, I say that, but out here, this is just farmland. So it's about the same level of rural in both areas. Same level of urbanization. So how do you like that? We haven't even really done any, you know, significant analysis here other than just looking at the data as it is. And we're already discovering these trends that are extremely striking. This is not a small variance. The turnout in southeastern Travis County was between 40 and 50%, between 30 and 50%. That's still extremely low compared to the overall turnout numbers. And those are majority Hispanic voting districts, probably. Probably at least 50% people that live in southeastern Travis County in those voting districts are Hispanic. And in western Travis County, we see almost zero turnout for Hispanic surname voters. And we can see that it's not that nobody, I mean, in many cases, it is kind of like nobody lives there, but there are like hundreds of voters that live out here, in each of these voting districts. There are hundreds. It's not to the level of 2,500, but so that's why they focused their efforts down here, right? It's because there's a much higher density of voters in these areas, so it's a lot less work to get more voters to turn out. But that doesn't explain why turnout in Pflugerville was so terrible. Was there just no outreach in Pflugerville? Is that what happened there? Those are really poor numbers. That's really bad. It's just a suburban neighborhood. You can hit a lot of houses, probably easier than you can in this area. And looks like it was just ignored. So that's interesting. It looks like voter registration in these areas are actually quite poor. There's a lot of Hispanic people that live north of Austin. Voter registration efforts up here, very bad. Very bad. Interesting. So if we compare that to the voter turnout as a whole, okay, first of all, we see those counties with significant Hispanic voting turnout still were below 50% turnout. Still bad. There's a couple like bright spots here, but this is bad, quite bad, right? The turnout in Pflugerville, on average, about 50%. Hispanic voters, 10%. That's pretty bad. You can see here in western Travis County, 80+% turnout. That's pretty amazing, isn't it? Okay, I need some water, so I'm gonna briefly go AFK and I'll be right back. All right, so that trend, it lines up with what we saw on the map of Texas too at the county level, doesn't it? In the Rio Grande Valley, turnout was extremely low. And you see Hispanic voters outside of one particular area where there was perhaps a lot of outreach, the highest density of Hispanic voters there, turnout was very low. So that is interesting because a lot of the story that I've read so far is that Hispanic voters turned out for Trump, but that might not actually be the case in aggregate. It could be that there's just a lot of non-voters, and the ones that wanted to vote for Trump turned out for Trump, and the ones that didn't want to vote just didn't vote. There's a lot of non-voting. Look at this. This graph is it's insane, honestly. Um, Even in the areas of highest turnout, it's abysmal. And also, just not turning out important areas like North Austin, Pflugerville, not turning them at all. Even the areas immediately around Austin, within Austin, the downtown area has like 30% turnout. The neighborhoods immediately surrounding downtown have 20% or less. That's a bad number. If we compare that to the number of voters, okay, so it's not high, right? But each of those tiny little districts has like several hundred people. I mean, I would say in this area, turnout is merely adequate. It's not even really adequate, but it's like okay, like if you could get half the voters out, that's like okay, right? And if you look at the proportion of turnout across the entire county, even in those areas where turnout is the highest for Spanish people, Spanish surname people, it's the lowest. It's the lowest in the entire county. And it's not close. So, what is the lesson so far? In Travis County, the 2024 election was 100% about turnout. The rich communities in West Austin turned out. Even the downtown communities in Austin really turn out. Those people are rich. It's absurdly expensive to live in downtown Austin. You look at these tight neighborhoods down here near downtown Austin, near the university, we're looking at 50% turnout at best. Compare that to Westlake Hills, 80%. 80%. The turnout in Pflugerville was below 50%. That's an important Democratic stronghold in this county. You have to turn those voters out. Total failure. East Austin, you have to turn it up. What are you doing? This is like a high target area. You have to turn these voters out. 40%. So that paints a pretty rough picture of what happened in Travis County. Let's do this thing that we were going to do and look at the voting tabulation districts with 0 Spanish surnames. Filter Spanish surname voter registration equals 0. I think I can just directly pipe it and say plot. I can use a dot syntax here, which will carry forward whatever is on the left-hand side of the pipe. It's actually not going to work very well. I can say, clean this up. Select geometry and Spanish surname. What's it called? I think this will work. Okay. So they're extant. This is like, you can see there's just like a couple of places where there's 0 registration. Zoom back over here. Some triangle that's here near Williamson County. No, it's not it. What is that? That weird looking triangle. Hard to even map onto what that is because it's at a weird zoom level. Those might, oh, I think it's actually that one. This is like downtown Austin. So these big western voting tabulation districts, there are voters out there. Now the sad thing is that so we really want better demographic data, right, at the voting tabulation district level. That's what we want. So here, the best we're saying we can do is basically target by Spanish surname, which, you know, is not really, that's not much, right? Like it's not much. So we want more that we can target on. We'd like to target much more specifically and much more accurately in each VTD. If you want to drive get out the vote campaigns, you're going to have to do a much better job. It has to be a personalized job. It has to be a message that resonates with the voter. And using county level data is not going to work, right? Because we can see that I mean, even just on one demographic factor in a county, there's way too much. You're not going to be able to do personalized messaging. You want to do Spanish language messaging in these areas. Really, like, come on, guys. We need to do much better. This is not good. But, you know, you need to target other groups as well. We need to turn out other groups as well. So, figure out how to get some more accurate demographic data here. There's a couple options. The first thing we can look at is the census voting or the census blocks. The census blocks might not correspond with voting districts 1 to 1, but we might be able to tabulate blocks and get pretty close to a voting district. So let's see if we can plot some Travis County census blocks and see what kind of information we have there. So let's read in census block data. Our shift right click didn't work. Let's try again. Path. Okay, so demo block, demo 2020 block SF. Block path. Demo 2020 block file. Just using standard syntax that we've been using. Well, not found. Somehow we messed it up. The slide? No. Somehow I misspelled it. Good. So there's a lot of blocks in the census data. $668,000 features. Nice. And let's take a look and see what that data looks like. So we have county, great. And then we have SCTB key. I think there is actually a box pop readme census. So lots of them. Blocks.zip, block key, county key, BIPS census county code, fine, census tract, census block. What I wanted to see was, what's this? SCTB key. So we have block group, state, county, tract, block. Oh, this is just an aggregation. State, county, tract, block, key. Got it. We have voting age population. Good. Right. So this doesn't have any of the demographics on it though. So this just has like the blocks and the key things. So we'll have to find, I'm guessing in blocks pop, we have some data here. Big file. It's not a big file. I don't know what's struggling about this. A couple tens of megs. Notepad no good. Okay, so this is what has all the good stuff, including the block key, SCTB key, all that good stuff. All right, so you want demo 2020 block read.csv. It's not the same path. Blocks pop text. All right, let's see if these conform. They have the same shape between these two data sets, or at least the same number of rows would be nice. They do. Surprisingly good data, honestly. Like, I was complaining a little bit about the naming conventions before, and that is an irritant, but the fact that these two data sets have the same number of rows, like, something you usually don't find. Actually taking time to most part here. All right, so let's join some. Join census block and VTD data. How are we going to do that? Because we don't have block on the VTD data. So we're going to have to do something like join the geometries, right? We're going to have to intersect the geometries somehow. And that's not going to be that's non-trivial. So let's think about what this is going to look like, right? Actually, before we do that, let's plot the Travis County census blocks and just get a sense of whether these look like the voting districts. Are they about the same size? And if they aren't, which is bigger? Are the voting districts bigger, or are the census blocks bigger? So we're going to use the shapefile, and we're going to join onto it the county data. Actually, maybe we can just use 300 voting districts in Travis County. It's 453. CNTY 450. So if I do something like filter CNTY equals 453, stored as a character. We get 17,000 blocks. Cool. So apparently this is a very finely grained unit, which means we might be able to tabulate them into voting districts. Now the edges might not exactly overlap, so we could have census blocks that span multiple voting districts. It's possible. And we're going to have to think about how to handle that. If we want to do any kind of aggregation, we might have to do some kind of like weighted something based on the amount of area that is overlapping. But this is all putting the cart before the horse. So let's just look at these census. This might take a while. Oh, not that bad. Okay, interesting. That's a cool plot, isn't it? Look at this. This is how our census data, how the government tracks who lives where. Really very cool. Look at that. It's really rather beautiful, isn't it? You can see Lake Travis. Very cool. I have it color coded by, I believe it's block group. And we can see there are 6 block groups in Travis County. And they're geographically discontinuous. Very bizarre. I don't know. That's interesting to me. I sort of wonder what a block group represents. Not really sure. But we see the very dense urban areas in Austin, South Austin, North Austin, very tightly packed block groups, or blocks rather. We can see the suburban areas, and say the Cedar Park area, the South Round Rock area, Pflugerville, North Austin. This is like, what are these neighborhoods? I can't remember. Something with a W. The stadium is maybe like up in this area somewhere. The Apple campus is like over here somewhere. Get a very good sense of all the road structures here as well. Even though we aren't plotting the roads specifically, we can see all the main roads, right? This is 183. This is 35. This is 290. This is 71. This is northern part of 71. I guess 71 comes down this way. Or does it go across? No, it goes across this way. I can't remember now. What is this? This is like Cesar Chavez. 71's down here. The river going like this. Lake Austin. Technically, this river is known as Lake Austin. There's a dam here and a dam here. Mansfield Dam And what is this one called? The T? Can't remember. South of that, Lady Bird Johnson Lake, formerly Town Lake. And here's Lake Travis. Into the Colorado River. We have the West Austin neighborhoods of Steiner Ranch, Hudson Bend, Apache Shores, Lakeway, Bee Cave. Bee Cave kind of extending all of this area, I believe. Very cool. Maps are awesome. Maps are just truly awesome. So the question we have is, if we aggregate these block groups, I want to take a union of these block groups and try to form something that approximates a voter tabulation district, right? So here are my voter tabulation districts. These are made up of multiple block groups, multiple blocks. And we can see that it might not, the edges might not, they might overlap, right? A block group could span multiple voter tabulation districts. And if that's the case, we're going to have to figure out some kind of a way to handle that, right? Because we have very nice demographic information in terms of the block groups. Well, at least we have some. And we don't really have any demographic information in terms of the voter tabulation district. So, yes, if I was to draw this, right? Like, hypothetically, we have a voter tabulation district that looks, say, like this, okay? And within this voter tabulation district, we are going to have block groups. And the block groups might look like this. Use a different color. The block groups might look like this. They're going to be adjacent to each other, right? Etc. Some are going to be fully contained within the voter tabulation district, and others may not be. And so if we use our shapefiles to intersect these two units, we have to think about how we want to handle these scenarios where the voter tabulation district and the block group don't match. So one thing we can think of doing, right, is, so what we want is the block to be related to a VTD. That's what we want. And we want to be able to say these blocks are within this VTD, right? VTD number 1 contains blocks 4, 5, and 6, right? Now that might not be the case because block 4 might be in VTD 1, 2, and 3, right? Like we could think of a scenario where, where neighboring VTDs actually kind of extend like this, right? So if this is a VTD, this is a VTD, this is a VTD, this block group could actually be within multiple VTDs. I don't know if this is the case, but it's probably the case. So one way we can try and check this is to look at a single VTD, plot a single VTD, and then intersect it, not intersect it, we want to join it with the block groups and plot every block group that is touching or within this VTD and see if the edges line up, right? Does this actually happen? Or are all the VTDs, maybe the VTDs were composed of block groups, right? So it's possible that when they were doing this, that the VTDs are actually, maybe it perfectly aligns. But there's things that happen, right? Voting districts change year over year, potentially. Blocks change from census to census. So, I don't know very much about this process. And these are just all situations that might be the case. But the only way to know is to just look and see if this kind of thing actually happens. And for that, we're going to have to use some of the geometry functions in the SF package. So there's a geometry function called SF touch, I believe. Let's look at these. Geometry operations is really what we want to know. Geometric operations. Create a, okay. So that we have contains, identify if y is within x. That's just a point though. Covered by, identifies if x is completely within a polygon. Polygon completely within polygon. Crosses. Identify if any geometry of x have commonalities with y. Covers. Crosses. So I think crosses is identify if geometries of x and y share space, are of the same dimension, but are not completely contained by each other. Overlaps. Touches. Identify if geometries of x and y share a common point. So we don't want touches because we don't want to know like if they just share a boundary. ST within identifies if x is in a specified distance to y. Not really what we want. We're probably going to need to... So the operation I'm thinking of is something like this. Identifies if x and y geometry share any space. And a union for the blocks. So think of an operation like this. We take a VTD and we use crosses on the geometries from the block groups. And we find all geometries from the block groups that cross a given VTD. We collect those. And then we plot each of those things. We plot the VTD and we plot the block groups, the blocks. And we see how closely those geometries line up. If it's a one-to-one mapping, that's like pretty cool. And if it's not a one-to-one mapping, then we can start thinking about this problem of intersections a bit more. So, first, we are going to use ST crosses to find all blocks that cross a given VTD. It is called ST crosses. Now let's just look up ST crosses and see the exact syntax. So it's going to return a matrix. So this is like a true-false statement. I think we might be able to do something like this. We might be able to say, well, first let's pick our voting tabulation district, right? Which one do we want to use? I really don't know. I don't even know how these are numbered. VTD 0100. Okay. So if we take VTD 0100, what we're going to do with this is say filter VTD equals 0100. And now we want to say something like VTD. We're going to take demo block SF. So this is all of our blocks. And we're going to say something like filter ST crosses VTD 0100. Just see what happens. Not sure how long this is going to take. It might take a little while. Oh, okay. Okay, it must be a logical vector, not a list object. Let's try something else here. Let's try, I think this is basically what I did before. Let's just see if we're even using this properly. Okay, we're getting something, but we'd like to return if it's true, right? I don't want all of the block groups. I just want to know which ones are true. Ask ChatGPT to help me with this, speed this process up. I have 2 sets of data of type SF. I want to use ST crosses to return all of the elements in one data set that are that cross the other. Something like this. Oh, I only want to return the elements that cross. Okay, so somehow we're close. Just see if ChatGPT correct. Not really. Yeah, it made a mistake. Okay, and then it just crashed out. This looks more similar to what I was expecting. But we got 0, so that's a bit of a thing. How can we get 0, right? Huh. Like, it can't be 0. So, something we're doing is not quite. We have this polygon. I wonder if the... Good work. Okay. All right. Okay. All right. So where are we? We're trying to intersect these things. I'm surprised ST crosses doesn't work. I'm confused. Let's just see what ST intersects does. And I feel like I'm just not using this the right way. Here. Do distance stuff. Touches, crosses. For every geometry pair, whether they intersect. Sparse equals false. See, this is returning like this matrix form, and mine is returning this sparse geometry. What if we say sparse equals that's what I'm expecting. Hmm. Hmm. So I was expecting something more like this, but instead I got no matches. Yeah, we do have some intersections. So try this. Column select. This is actually row one. Okay, so what? What are we doing here? Crossing blocks. Let's see if we got them. Looks like we got them. So let's plot them. Let's just plot like that. Actually, let's plot like 1, 2. Plot this. Okay. So the issue we were worried about is in fact real. If we compare this to this shape, say this compared to this, you see here they were successful and able to do this. So let's see if we just copy this. It doesn't do it. It's so frustrating, actually. Whatever. It's because of the legend. No, it's not because of the legend. I don't know why this is not working. Very frustrating. I wanted these to be adjacent, but whatever. We can see by going back and forth that I'm going to clean this code up a little bit. This. Okay. So we can see that the shape, this boundary problem is real, right? That's the thing. The boundary problem is real. So how are we going to handle it? That's the real question. And it's even very strange, right? Like, okay, so like these blocks are probably like look at these strips, right? That's very strange. It's very strange geometry here. Very interesting, but very strange. Man, I'd really like to plot these two images on top of each other. Maybe ChatGPT play with this. Simply doesn't work. Excuse me. All right. In any case, it doesn't work. I wonder if ggplot can work with these geometries. I bet it can. See what happens here. X, Y, and ID. Let's see. Geom SF. That's very cool, isn't it? ggplot2, so great. Okay, so we have these blocks. And now I want to overlay geom SF data equals etd 0100 alpha color equals black. All right. That's pretty cool, isn't it? All right. So we can see that we've got some weird geometry stuff that we have to deal with, right? I'm going to change this color to red. There we go. Now we can really see what we're dealing with. And what we're dealing with is blocks of an unusual size, right? I don't want to zoom in. We can see some of them line up quite nicely. And to my eye, these are distinct, right? What I actually see is intersects. Let's instead of intersects, let's use crosses. Let's just, right? Lots. It's it doesn't work. Crosses doesn't work. Why is that? Because intersects is like counting the shared edge, and I don't want it to count the shared edge, right? So I really don't want it to count the shared edge. Why doesn't crosses work? That's the other thing. I'm not really understanding crosses, ST crosses. We could try ST join. ST covers. Where are the list of these? I need the list. I need the list. Surely these don't just... SD covers if any... identifies if any point from X is outside. Any point from X outside. It seems like a lot of those should be true, doesn't it? Because most of the blocks are outside of Y. Share any space. Overlaps. Touches. We want to like... It's like intersects minus touches, right? Identifies if any geometry of X have commonalities with Y. It's so interesting when they choose to use verbs or adjectives like that, have commonalities with. Like, why would you say that? Commonalities. Like some of them obviously have quote unquote commonalities, because if we use intersects, it returns a non-zero set. So what does commonalities actually mean? Very confusing. Nevertheless, apparently they don't have any commonalities. Really don't understand what that means. If they share any space. So it's not so much that I want to identify when they share space. Maybe I can... So it's sort of like if intersects equals true and touches equals false. Right? That's kind of... Seems like that's kind of what I want. Think about doing. Demo block SF. Mutate. Intersect. 1, 0. touches. Right? Something like that. Oh, wait. I'm confused. I think we can. So we're trying to create vectors of the same length so that we can stack it on the data set. Now see our edges here, ST touches. Doesn't have the same length, right? That's a problem. There, it does have the same length. Okay. So this should work. Okay. Yeah, I understand that. But I hope this really did what I wanted it to do. See, it's stored as a matrix value, which is actually nothing that we want. So in theory, we should say something like as.vector. That. That gets rid of that warning. And now if we plot this, that's pretty cool, isn't it? Ah, okay. I think that the census blocks line up with the voting district. At least this one does, right? This is pretty cool, man. This is pretty cool, man. All right, just need a quick snack. I'll be back. Okay, so this is pretty cool. We've got our voting track, voting tabulation district 0100, and we have all the census blocks that make up that voting tabulation district. Isn't that cool? It's so interesting. Now we did that by calculating. We had to do a two-step calculation here, which just seems wrong to me, but like, does st-intersects have an option to not include edges? That's what I want, right? Disjoint covers covered by equals exactly. Maybe ChatGPT can answer this question. Is there a way to simplify this geometric operation? I didn't give it all. Oh, interesting. Use strelate. F triple star T quadruple star means the geometries touch at their boundaries but do not overlap. Let's look at strelate. Can I use strelate to identify geometries that intersect but do not simply border? Proper intersects. It's a bowl scraping good time. Okay, this is interesting. Pattern. We can try this. Write me a function that will time and of our code. Okay. Let's just play around with it and see. First, if they give us the same result, and then if it's faster. Correct number of actually say like bars as dot vector. Geometry and ooh, check this filtering code to the plot. Eight. Okay, so first let's look the same as it. Make sure. Okay, that does. I still think that's so cool. Okay, and let's check if this proper intersection results in the same shapes. Okay, it does. So that's cool. Now, we're looking at a voting tabulation district here, right? So we're really zooming in. We started at the county level, we went down to the voting tabulation district level, and now we're at the census block level. And we can actually get very specific information about who lives in these census blocks, down to about, you know, tens of people. And that should be very powerful in determining, you know, who voted for who. And we could even, you know, think about how we would target voters in certain census blocks to perhaps drive turnout in the future, right? So that's a possibility. And actually do the timing. Time kind of curious. Time geometry calculations. Yeah. Don't forget to like and subscribe. We're going to time our geometry calculation. So that's kind of cool. Don't forget to like and subscribe. All right, so in order to do that, what are we gonna actually do here? We're just gonna run time code. We're gonna run this statement. See what happens. Yeah. Okay. It returns everything. Just change that to return the time. Maybe not, I don't know. Returns the result and it prints the time. That's fine. So it took 6.8 seconds to do that. And I pass it multiple statements. Probably not. I wrap it like this. .23 seconds. So this strelate is much, much faster. Interesting. So we can call this underlying function, and we can use ChatGPT to help us determine the pattern when we need to do these complex operations involving lots of census blocks. Now, so this census block seems to be fully contained this VTD seems to be fully contained by these census blocks. We don't know that that's true for all census blocks. So, that's something to think about. But nevertheless, we soldier forward. All right, so what would we want to look at here in terms of the demographic data for each of these, right? I'm going to change this function print f time code expression return if return all right, so now we can pass this return value if we just want to return the time. No big deal. All right. for example. It should just return the time and not print out the whole result of the code. Yep, 7 seconds. Notice how there was a variance there of about 0.2 seconds. That's interesting. I guess because, you know, my computer's doing a lot of stuff, and it's not going to take the exact same amount of time every time. On a dedicated machine, I imagine it'd be somewhat consistent. All right, so what now? Now we want to bring in some of the voting data, or the demographic data and the voting data, and see how we can analyze this stuff. So I'm actually going to subset this data. Filter. Filter what? Cross proper intersects equals true. Yep. And then we're going to do something else. We are going to join our demographic data on, I guess, SCTB key. So inner join. Demo, I believe it's demo 2020 block. Yeah. No. Yeah. Okay. We could use FID, I suppose. No, we can't. So we don't have FID on this data set. But we do have SCTB key, which I think is the proper join key. So from blocks 0, 1, 0, 0, we actually don't want everything. So we're going to select SCTB key. We want the geometry. Let's take the shape, area, shape, length. The county key is all consistent. Census tract block key, like, doesn't really matter. None of this other stuff is really important. We just need the join key, because this is just the shape file. It just is like, these are just the blocks, this is the shapes. And all the important information is going to be on this joining file. So we're just going to take the geometry and the join key. And we're going to join this data file, and we're going to say by equals SCTB key. And we're going to save that as blocks 0, 1, 0, 0. That's our voting tabulation district of interest. Demo. There we go. Ooh. What happened? SCTB key is character, SCTB key is double. Interesting. So in the first it's saved as a character, the second is saved as a double. So we're just going to say mutate SCTB key equals as a character SCTB key. This should take care of that. And there we go. Now we have all of our voting tabulation district 0100. We have all of the demographics, don't we? So let's ggplot data equals blocks demo geom sf what should we look at? Well, we were looking at Hispanic voting proportions before. Oh, you know what we don't have here? Are the voting. We don't have voting type, right? So it sort of points in the direction that this analysis can go, right? So the lowest level data we have for voting data is the VTD. So we can identify VTDs that have parameters that are important to us, like low voting turnout, say. And we can then look at the demographic characteristics of those districts. Now you might wonder, like, which of those is more important, right? So we can look at the voting tabulation district as a whole and say these certain demographic groups are important to us in terms of voting, and we want to turn out those voters. And so in order to do that, we're going to drill down into the census block level and identify where those people live within that district. But what we can't do is drill down to the census block level and see how many of those people voted for in the last election. Census block level data for voting, in other words. We don't have that. So the best we can do is just identify areas of potential interest and then go after them. This raises a lot of questions, right? It raises questions like, should you be targeting voters based on demographic data? Every campaign does this. And maybe you shouldn't do that. Maybe you should come up with a better way to target voters. And I'm open to those ideas. But right now, the data I have is demographic data. So we're going to look at that, and we're going to compare it to the voting data that we have. And if we think we can do better by supplementing with other data, whether that's economic data or I don't know what else we could possibly think of, then we're going to do that. But the first thing is just to use the data we have. So that's what we're going to do. Now, I don't know what this VAP column is in here, and I want to know. So we're going to look that up. Voting age population. Okay, so that's actually an interesting and relevant statistic. Voting age population. Now you might say, okay, we're not going to target specifically based on how many people of a certain demographic there are in that district. I think you're going to get into problems if you do that as a campaign. But what you can do is target voting blocks with specific types of information based on who lives there, right? If you know that the voting age population is predominantly Hispanic in this census block, then you can you're targeting whether it's mailers or I don't know what, you can. So this is another good question, right? Like, how are you actually targeting people? If you're using mailers, which is probably a bad strategy, but I don't know. You can target very specifically based on who you know lives there. If you're targeting using online ads, the granularity for that is not as precise. You can't target a specific household with online ads. You can't target a specific census block with online ads, as far as I know. You can't say, I want people that live in this geographic locale, because all your data gets routed through a service provider, and whoever you're buying ads from doesn't have the level of granularity below the service provider, right? Like, they don't have much information beyond that. They know kind of like generally in the region where you're coming from, and that's about it. So that really hampers your targeting strategy, right? So in this world where, most advertising is online, how do you use this lower level demographic? How do you use it? Do you just use it to understand what happened in the previous election? Voters in these districts they stayed home. They had these demographic profiles. The demographic profiles we could do like a principal component analysis on the demographic profiles of the voting age population in the census blocks where the turnout was low, and see, who stayed home, who didn't stay home, stuff like that. I guess we'll just have to move one step at a time. So let's just do some plotting, and that'll be where we end today. Got a nice productive day where we made some very interesting plots and worked with the GIS data. Then maybe tomorrow we can get started on some GIS visualization using dashboarding, which is going to require us to write some functions that do the basic things we do now, and then take the dashboard input as input to the functions. So that'll be fun. So let's just plot the Hispanic voting age population in all of the voting blocks, census blocks in this voting tabulation district. So what we want to do is say fill equals Hispanic voting age population. Must have misspelled it. HISPVAP. No, I didn't. Oh. Confused by that. Why isn't it recognizing my... Do I have to like... Okay, weird. Must be positive. Colors codes must be positive. Surely 0 is allowed, right? No? Why would 0 not be allowed? It's very weird. Like color, like this is allowed, but fill isn't? Weird to me. There's something I should be using besides fill? This isn't really what I want. Equals area. Is it like not a integer? Or can we say like as numeric? No. So weird to me that they won't allow 0 values here. Like here, there clearly is a 0. Why would it not allow 0? It's just so weird to have a numeric that doesn't allow 0 values. I have to put that in an aesthetic. Fill equals this. Yeah, okay. There we go. Look at that. How's that for spatially non-random, highly segregated population? Total divided by BAP. This is the proportion of voters in each population that are Hispanic. 100%. Only Hispanic people. Interesting. Some of these census blocks, apparently no one lives there. Or no voting age population, which should imply no one. Yeah, look, total 0, 0. Looks like it's just east of the highway somewhere. If I had to guess, that's what this thin strip is. Library patchwork. I'll let me stitch plots together. I need to set the default behavior to be packages that don't solve from. All right. So here's plot number 1. Proportion of BAP stuff's getting up. Let's do these back. Back. Blow this up, shall we? So here we have one voting tabulation district, and we're looking at the Hispanic voting age population. So we can see that the number of Hispanics of voting age is concentrated in one particular block, really just a couple blocks. And the proportion of voting age population that's Hispanic. Okay, well, this is interesting. I mean, this is the kind of demographic information that we can pull up. Now, the question is something like, in voting districts that had low turnout, what is the demographic makeup of those voting districts? And can we target people specifically of the voting age population in those districts? And if so, how should they be targeted according to their demographic breakdown? And you can see that there's a lot of heterogeneity in the voting age population within these census blocks. Some have a lot of people living there of a certain race, others don't. So there's definitely, we're just scraping the surface of how to look at this demographic data. And as we go forward, we're going to try and develop tools that allow us to look at any voting district, analyze it by census block, and understand who lives there. Over time, we might be able to bring in additional data. That'll be very interesting to see if we can do that. Anything that's correlated with census block, essentially, we'll be able to bring in. We might even be able to use some county level data and things like this. But as we can see, that the spatial distribution of the people is not even across the counties. So we really have to understand at the voting, even within voting tabulation districts, it is not spatially homogeneous. There's gross heterogeneity within voting tabulation districts, who lives there and whatnot. So this will be very interesting going forward to really understand at a micro level who's living in each voting district in order to better understand how we can actually target those voting districts to enable get out the vote efforts in those areas. All right, I think that's going to be it for today. What have we done? Well, we started with a county level map of all Texas voting patterns. We decided to drill down into Travis County, and we made a map of Travis County that showed Oh, it's not showing here. Let's see if we can pull it up quickly. We made a map of Travis County. Plot turnout in VTDs from a selected county. Here we go. We made a map. I wish it would plot. I'm not sure why it's not doing that. We made a map of Travis County and looked at it by voter turnout in each voting tabulation district. And then we looked at it in those voting tabulation districts by Spanish surname to see where the higher proportion of, oops, that's this one. How the voting proportion, or how the voter turnout was according to Spanish surnames. Then we opened up the census block data and plotted all the census blocks in Travis County. What a cool map that is. And then we joined that data with the VTD data to plot the census blocks that comprise a single VTD. That's right here. Finally, we joined that with some demographic data to plot the proportion of voting age population that is Hispanic within each census block in a VTD. And moving forward, we're going to try and create a tool that will take a map such as this Travis County map and allow us to zoom in on a particular VTD and understand the demographic profile of that VTD. All right.